Hello everyone, and welcome to this lesson on the trapezoidal rule in calculus and numerical integration. So far in the calculus, you have hopefully learned about Riemann sums and using rectangular approximations for finding area under a curve. And you probably have learned also how to find definite integrals to model areas under a curve by such basic integration methods as U substitution, the general power rule for integration, etc. The examples you see here are two that you cannot do with algebraic methods at this point in your calculus career. So we need another way to evaluate them. Since the fundamental theorem of calculus cannot be applied, perhaps we could apply some numerical methods that you've seen to approximate the definite integral. Those would be the left endpoint approximation, the right endpoint approximation, or the midpoint approximation. These all are examples of rectangular approximations to area under a curve, as they involved us inscribing or circumscribing rectangles around the curve or beneath the curve in order to approximate the area under the curve. You might remember, though, that these rectangular methods don't always offer the most accurate approximation of these definite integrals, of these areas under a curve. You might recall that they often yielded a good bit of positive or negative error. The idea behind the trapezoidal rule we are going to explore today is that instead of using rectangles to approximate the area under a curve, we use trapezoids. Trapezoids allow for less empty space, less negative error than what we encountered by using inscribed rectangles that also resulted in negative error, and also less error than what we saw with the positive error that resulted from using circumscribed rectangles. So let's develop the idea. We have a continuous function f of x on a closed interval from a to b. Now if you turn your head sideways to the left, you will see that we do indeed have inscribed trapezoids beneath this curve. The number of trapezoids is what you will often see referred to as the number of subintervals, just as we saw with the rectangular approximations. Now, one key characteristic of the trapezoidal rule is that these trapezoids are all of equal height. And when we talk about the height of the trapezoids, we are referring to this distance right here, that horizontal distance. It is important for you to remember that the heights of the trapezoids in the trapezoidal rule are all equal. You will come across other problems that ask you for a, quote, trapezoidal approximation, end quote, in which those trapezoids are not of equal height. That is not a pure trapezoidal rule. So according to the trapezoidal rule, the height of each trapezoid can be obtained with the formula b minus a all divided by n, and we refer to this as delta x. N is the number of trapezoids, the number of subintervals that you want to have. So we are going to derive where the trapezoidal rule comes from in the calculus and the formula associated with it. So think back to your geometry days. How is it that we would get the area of a trapezoid? Hopefully you remember that area of a trapezoid is given by the formula 1/2 times the height times the sum of the bases, which we designate as b sub 1 and b sub 2. What we're going to do is return to our diagram, go one trapezoid at a time, and derive what the trapezoidal rule actually states. So let's start on the far left. For this first trapezoid, we would have 1/2 the height. Now remember, the height of the trapezoid is this horizontal distance, which we referred to as delta x. It's b minus a all divided by n. We're just going to refer to it as delta x here for simplicity's sake. Now we need to multiply by the sum of the height of the bases. Now this top base of this first trapezoid is given to us by the function value at a. So we're going to designate it as f of a. Plus, now we need the bottom base, whose length is given to us by f of x sub 1. So that's the first trapezoid. Moving to the second trapezoid, once again we have 1/2 this height, which we designate as delta x. Now for the sum of the bases. Now notice how the top base of this second trapezoid is the same as the bottom base of the first trapezoid. And remember, that height was given to us by f of x sub 1. Plus, now we need the bottom base of the second trapezoid. Now let's refer to this as x sub 2. We don't have that in there in our diagram. So that's the second trapezoid. Moving to the third trapezoid, once again we have 1/2 this height, designated by delta x. And as we saw with the second trapezoid, notice how the top base of this third trapezoid is the bottom base of the second trapezoid, and that was given to us, recall, by f of x sub 2. Plus, now we need the bottom base of that third trapezoid. Let's call that x sub 3. And that height, the length of that bottom base, is given to us by f of x sub 3. Now we would continue on in this manner. Now let's jump though to the very last trapezoid. For this last trapezoid on the far right, we would have 1/2 this height, which is still delta x, times the sum of the bases. Now we would need to designate how we would obtain this length for the top base of that last trapezoid. Let's refer to that as, maybe we call this one x sub I instead of this one. Plus, and now the bottom base of the final trapezoid is the function value at b. So we would have f of b. Let's try to simplify this. You'll notice we have 1/2 delta x in each of these, so let's factor that out as a greatest common factor. And once we do that, notice what we're left with. Except for this f of a and the f of b, notice how each of these other lengths show up twice. For example, we have f of x sub 1 here, but we also have it here. We have f of x sub 2 here, and also here. If we had continued on, in addition to this f of x sub 3, we would have had another one, and we also would have had another f of x sub I. That's because each of these lengths is doing double duty as the bottom base of one trapezoid and the top base of the next trapezoid. So the way in which we could summarize this is we have to multiply 1/2 delta x by f of a, but then really what we have is 2 times each of these other lengths until we get to the very end, the very last trapezoid, and the bottom base of the very last trapezoid, where we have only f of b. So as I mentioned, except for f of a and f of b, everything inside is doubled. And that brings us to the official statement of the trapezoidal rule. The trapezoidal rule will state that the integral from a to b of f of x dx, the interpretation of which is the area under the curve of f of x from a to b, is approximately given by b minus a over 2n. Now that's where you could easily think of this as 1/2 delta x if you prefer, times f of x sub 0, and x sub 0 is your a value, plus 2 times f of x sub 1, plus 2 times f sub x sub 2, plus so on and so forth, all the way up to the very end, where we have f of x sub n, where x sub n is your b value. Please do take note of the fact that the trapezoidal rule only provides us with an approximation of that definite integral of the area under the curve. Therefore, use of an approximately equal to symbol is absolutely necessary. It is perfectly fine if you prefer the equal sign with the dot over it or the 2 squigglies. Either one is fine. Now let's talk a little bit about how this trapezoidal rule and the approximation it provides for the area under a curve compares to that approximation we receive by doing a midpoint approximation by using rectangles. And really what it depends upon is the concavity of the curve itself. Let's begin with a function that happens to be concave down. So perhaps the curve is shaped like this, and it would be on an interval from a to b, and let's make this easy and just do like 3 subintervals. Now, if we were to do a trapezoidal approximation, the first trapezoid would have a base here, the second base would be here, and if you turn your head sideways, the right side of the trapezoid, the slanted side, would go like that. Notice there's a wee bit of negative area in there. If we did the same thing here, once again we have a wee bit of negative area, and then the last one, once again we have just a little bit. So what ends up happening is that if the curve is concave down, the trapezoidal approximation is less than the value of the real integral of the true area under the curve. Now, if we were to consider a midpoint approximation, remember that according to the way in which we draw a midpoint approximation, it means as we draw our rectangles, it's the middle of the top of the rectangle that hits the curve. So for this first rectangle, the first rectangle is going to come up like this. Here's the middle of it, so it would look like that. Now notice you do have a little bit of positive error, you got a little bit of negative area there. In the second one, this one was almost rectangular to begin with. And then the third one, once again, you have a little bit of positive error and a little bit of negative error. It so happens, however, that the positive error outweighs the negative error. And what happens is that if the curve is concave down, the midpoint approximation is greater than the real integral. It's greater than the true value of the area under a curve. Now let's take a look at what happens if the curve is concave up. So if it's concave up, perhaps it's shaped like that. Once again, we would be on an interval from A to B, and once again, we'll keep it simple with just 3 subintervals. Let's consider first the trapezoidal approximation. The first trapezoid would have sides here and here. And when we draw this slanted side, see how it's just lying a little bit above the curve? So this has all positive error here. The same is going to be true of the second one. It's just a wee tiny bit of positive error. And then the same for the third. Sort of right, I drew it a little exaggerated. So what happens is, in this case, when the curve is concave up, the trapezoidal approximation is greater than the real integral. It's greater than the actual area under the curve. Considering the midpoint approximation, remember that it is the middle of the top of the rectangles that has to hit the curve. So the first one's going to come right about here. And notice once again you have this little bit of positive error, but you got a good bit more of negative error here, right there. If we consider the next one, looks like the positive error and the negative error are a little bit closer together on that one. And same true is here. In this case, however, it is true that the negative error outweighs the positive error. And so a midpoint approximation, when the curve is concave up, is less than the value of the real integral. It is less than the value of the true area under a curve. So just something to think about in terms of how the concavity of the curve can definitely affect the comparison of a trapezoidal approximation to the area under a curve with a midpoint approximation. To wrap up today, we're going to talk about Simpson's rule, which is another numerical method for determining and approximating the area under a curve. It generally is true that the trapezoidal rule is more accurate compared to a right endpoint approximation or left endpoint or midpoint approximation. Simpson's rule, however, is considered one of the most accurate numerical methods out there. It is named for the British mathematician Thomas Simpson, who lived from 1710 to 1761. Recall that in the trapezoidal rule, successive points on the curve are connected by straight line segments, therefore forming our trapezoids. In Simpson's rule, these points are connected by parabolic segments, which I think you should be able to see pretty clearly here. You can see the dotted lines here are curved. So in a trapezoid, those were straight. In Simpson's rule, however, these are parabolic curves on the tops of these otherwise rectangles or trapezoids, however you want to think of them. What you see in boldface is the actual function whose area under which we are trying to approximate. And as you can tell that in this case they are equal subintervals. That is a key characteristic of Simpson's rule, just as it is with the trapezoidal rule, that all of these are of equal width. But at the top, instead of straight line segments, we have parabolic segments. That's what serves to create a more accurate approximation of the area under the curve. So this is really just for your knowledge. You do not have to know how to calculate Simpson's rule by hand. If you happen to have one of the graphing calculator programs called IntMeths, you'll notice that Simpson's rule is one of the approximations that you are provided with.